The goal of this lecture is to give you a sense of how recurrent neural networks are actually used for language modeling in practice. Last time we talked about using a recurrent neural network on the problem of predicting the next word in a sentence. We picked that example in part because it gives us an easy way to demonstrate how a recurrent neural network can operate, but also in part because that's a common pre-training task used on recurrent neural networks. If we want to use an RNN for a more interesting task like question answering or machine translation, then in a transfer learning type approach, we might first train it on a predict the next word type of problem, and then fine-tune it for the particular task that we're interested in. So the first topic we should consider is how can we get something more interesting than just a next word prediction as output from an RNN. And the key idea is that these hidden activations that we're passing back into the network, or when we unroll the network that we're passing forward in time, are actually the state that we really care about. We can think of this predict the next word task as a throwaway pre-training like we did for word embeddings. And then when we actually apply a recurrent neural network to a problem, what we're really interested in is this output here. That is, if we want to take some text as input, say a sentence that we're trying to translate to some other language, then we can give each word in the sentence to the recurrent neural network in order, and then once we've given all of the tokens in that sentence to the network, the hidden state that is produced at the last time step is a representation of the entire text that we've given. And so then we can feed this hidden state that comes from the last time step and represents the entire text from the neural network's perspective into some other neural network layers that will solve the task that we're interested in solving on the text that we were given. So if we were trying to classify the text, we might give this representation of the text to a few feed-forward neural network layers that can perform classification. But if what we want is a text as output, then we could do something like inverting this text input that we've done to produce the output. So we're now thinking of this entire process of feeding a whole sentence or a whole text of some sort to a recurrent neural network as a way of encoding that text into a neural network hidden layer activation state that we can then do subsequent processing on. And so we can now build another similar neural network that will operate as the decoder. So we can encode a sentence into the state of the neural network by feeding each token in that sentence into the recurrent network. And so in this encoding process, we are ignoring the outputs at all of the intermediate time steps and simply taking the activations at the end as an encoded representation of the entire text. Then we can have a second recurrent neural network that we train to take as input this encoding of a text and produce one token of output at a time. And as the state gets passed back into this decoder network, it will update along the way, allowing us to produce the next word of the output sentence. And so we can train this pair of recurrent neural networks to take in a sentence of text as input and then produce another sentence of text, either a translation into some other language or an answer to the question or a next line of a story as the output. The trouble is that we said last time that we were using 10H activations in these recurrent neural networks, And we know that tanh functions are subject to vanishing gradients. And so if we want to translate anything much longer than this very simple sentence, we are going to have problems with training such a big network with tanh activation functions. Simply because the tanh activations will make it hard for errors to propagate far back through either of these recurrent neural networks if we have a large number of time steps. The core idea to how this problem is solved has a lot in common with the idea of residual networks that we saw for improving deep convolutional networks, which is that we want to create a path that the gradients can take backwards through the network that is subject to far less squishing by tanh activation functions, and therefore lets gradients propagate all the way through a long encoding and decoding sequence. We can achieve this by modifying the recurrent neural network to have multiple paths that activations can take that are specifically designed for the purpose of encoding the information in the text and allowing gradients to propagate back through the network. The LSTM layer illustrated here achieves this goal of allowing us to encode and decode long sequences of text by allowing gradients to propagate efficiently backwards through the recurrent network. We have an input and an output to the recurrent layer that we can use, like we talked about last time, to train on a predict the next word task or other pre-training of the network. And the input here gets concatenated together with one of the hidden states that were passed along from the previous layer. And so we can think of this bottom input as corresponding to the hidden state that we're passing along in the plain recurrent network before. But we also have this additional hidden state C that we are passing along from the recurrent network to itself on each time step. So the main path through this network that corresponds to a vanilla recurrent network is that the hidden state and the input are concatenated together, and then they go into this tanh layer, which is a fully connected neural network layer with learnable weights. And then that is eventually passed through here and becomes the output of this particular time step and the hidden state that is passed along to the next time step. So this path through the layer corresponds to the simple recurrent neural network. So the previous hidden state on this green path gets concatenated with the current input and then passes through one fully connected layer with tanh activations. But we also have several fully connected neural network layers with sigmoid activation functions, and for each of these sigmoid layers, their output goes into an element-wise multiplication. We know that sigmoid activation functions output a value between 0 and 1. And since each of these sigmoid layers is being element-wise multiplied with some other tensor, we know that the result will be whatever other tensor we had, all of its elements will be multiplied by some value between 0 and 1. And so we can think of multiplying by 0 as forgetting that element of the previous activations. we can think of multiplying by 1 as remembering that element, and multiplying by something between 0 and 1 as partially remembering it. And so we can think of each of these sigmoid layers as learning what part of a previous activation do we want to pass through to subsequent computations, and what do we want to forget. So for example, this first sigmoid layer is telling us of the hidden state C that we got from the previous time step, which part do we want to forget? And we can think about this second layer as learning of the outputs from the tanh based on the input from the previous hidden layer and the inputs concatenated together. What part of the tanh activations do we want to pass along, and which parts do we want to ignore? And here we are adding together the H and C portions of the network, and then passing them through a tanh activation function. But of note, this tanh is not a learned layer. It is simply an activation function applied to this addition to squish it back to the range -1 to +1. And then the output of that tanh will have another sigmoid element-wise multiplied with it to determine what do we want to pass along and what do we want to forget. So each of these sigmoid layers applies to the previous hidden state and the current input. Those are concatenated together and fed into the sigmoids. And each of these is a fully connected neural network layer with learnable weights. And so we will be learning how to, based on the previous state and the current input, decide what information we want to pass through each of these element-wise multiplication operations. So we can think of these sigmoid activations as gates that decide what information we want to allow to pass through versus what information do we want to cut off. And the functioning of those gates is a thing that will be learned from the training data. So the important deviations here from the plain recurrent neural network are that we have some control of what information gets passed along and what information gets blocked based on these learned gates. And so these gates control what portion of the hidden state combined with the new input gets passed along to the next time step in the recurrent network. But then we also have this additional C hidden state that is also getting passed along to the next step, and this C output does not directly pass through any activation function. And so, if we follow the path backwards through the time steps of the recurrent network, this C path allows us to propagate gradients backwards through time without the decay of a tanh activation function. But at every time step, this C path does get combined with the H path, and so the learned encoding that corresponds to what we had in the previous version of a recurrent neural network is getting incorporated into these C's at every time step. And so we can think of these first two sigmoid activation layers as learning how do we, as a function of these two inputs, want to combine the C path with the H path at each layer. We could, in principle, based on some particularly important input, decide that we're going to have lots of zeros here and forget most of the information from the C path, and presumably at the same time we would want to pass along more information from the path where the new input has come in. And so these gates give us the opportunity, as we are taking in new information later in a text, to forget old information that is less important to the encoding of the overall text. Of note, in practice, we don't actually know what functions each of these internal layers will be learning. They are made up of parameters that will be trained by stochastic gradient descent. And so in much the same way that with convolutional neural networks, we don't actually know what each of the feature detectors is computing, we don't actually get to decide what function each of these gates and the tanh layer is computing. But we have set up the architecture in such a way that we think it has the potential to learn useful types of functions. In addition, in analogy to residual networks, we have two paths through each component of the network, where in residual networks we had the path that went through the block and the shortcut path that went around the block that then got combined. Here we have the H path that goes through the tanh activations and the C path that doesn't have activations applied directly. And so these two paths give us both the ability to do interesting computations within a particular LSTM time step and the ability to propagate gradients rapidly backwards through many applications of an LSTM network. So in summary, there are some theoretical justifications behind the architecture choices of an LSTM, but the reason that they are so widely used is that in practice they have found to be effective compared to other types of recurrent neural networks.